Hello everybody. In this PowerPoint aided video presentation, I will try to give an intuitive understanding to the standard discrete probability distributions like binomial, Poisson and so on based on the Bernoulli experiment. The prerequisites for this video presentation are the basic concepts of probability, the axioms of probability such as addition law, multiplication law, fundamental concept of random variable, mean, variance, and combinatorics, particularly the combination used as a tool for problem solving in probability. So these are the fundamental concepts that are prerequisites for this particular video presentation. Here I have tried to give my understanding of the concepts of discrete probability distributions that I have conceptualized over the years to teach my students. In this presentation, we will have the following contents. I will start with a brief introduction to Bernoulli experiment, the notation that we will be using throughout the PowerPoint presentation, and then binomial distribution, Poisson distribution, geometric, negative binomial distribution. Finally, a few problems just for the identification of what distribution to use and a summarization of the PowerPoint presentation. Let me start by defining what is called as a random experiment. Any experiment for which the final outcome cannot be predicted with 100% probability is called as a random experiment. All the outcomes of the experiment are known to the person who does the experiment, but what outcome will finally come or finally result in the experiment is not known. Wherever there is a randomness in the final outcome of an experiment, such experiments are called random experiments. Experiments for which the outcomes can be predicted with 100% probability are called deterministic experiments. Random experiments are also called as stochastic experiments. The throwing of a dice is a random experiment because all of us know that 1 out of the 6 numbers from 1 to 6 is going to show up as the final result. But which out of the 6 is going to come cannot be predicted. Tossing of a coin is also a random experiment because we know that head or tail is going to occur, but which out of the two is going to occur cannot be predicted. Such experiments are random experiments. A particular category of random experiment is the Bernoulli trial or the Bernoulli experiment. Any random experiment for which there are only two possible outcomes are called Bernoulli experiments. For convenience, one of the outcome can be called as success and the other outcome can be called as failure. Experiments for which there is nothing other than success and failure as the final outcomes are called Bernoulli experiments. Writing an examination is a typical Bernoulli experiment because there is an outright pass or an outright fail as the final result. Of course, here I am not considering examinations that are conducted for the sake of improvement of marks. Similarly, throwing at a target is also a Bernoulli experiment because we either hit the target or we miss the target. Only two possible outcomes are there, and therefore that again is a Bernoulli experiment. It is conventional for us to use the success probability by P and the failure probability by Q. Because there is nothing other than success and failure, the two probabilities will sum up to 1. That is, success and failure are mutually exclusive and exhaustive in a Bernoulli trial. Thus, P plus Q is always equal to 1. By imposing certain conditions on a set of independent Bernoulli trials, we get various discrete standard distributions. That is, by imposing conditions on the number of successes or on the number of Bernoulli trials, we get the standard distribution such as binomial, Poisson. We will be dealing in detail about these 4 distributions in the slides to come. The presentation scope is restricted only to binomial, Poisson, geometric and negative binomial distribution. One needs to understand that there are other standard distributions of the discrete type such as hypergeometric distribution and multinomial distribution. Perhaps I will come up with another presentation dealing with these two distributions. In this presentation, I am going to deal only with these 4 standard distributions. The notation that I will be using in this presentation will be N for representing the number of Bernoulli trials, P for probability of success, Q for probability of failure, and X for the number of successes, and X here is the random variable. P the probability of success and X the number of successes are interlinked. If P is defined as the probability of success, then number of successes must be the random variable X. That is, they are closely associated representations. Let me start with the binomial distribution. The binomial random variable capital X has its probability function or probability mass function defined as NCX P power X Q power N minus X. It characterizes a specified number of successes in a specified number of Bernoulli trials. Wherever the success count and the trial count are known to us, we use the binomial random variable for such kind of problems. X represents the number of successes, which means small x is the values taken by capital X, which is 0, 1, 2, 3, so on up to n. Please observe that the random variable can take only value up to n because we are only doing n trials in this particular experiment. When x is 0, it means that there have been no successes at all in all the n trials, or all n trials have resulted in failures. When x is 1, 1 out of the n trials is a success and the remaining n minus 1 trials are failures. When n is 2, 2 out of the n trials are successes and the remaining n minus 2 are failures. So when x is n, it means all n trials have resulted in successes and there have been no failures at all. That is 0 number of failures. So we can understand here that every value taken by the random variable gives us dual information, two-part information. One regarding the number of successes and the other regarding the number of failures. See that X will give us the explicit information about the success count and N minus X will give us the implicit information about the failure count. Now if there are X number of successes and N minus X number of failures, then by a direct application of multiplication law, we know that the probability is P power X into Q power N minus X. We are multiplying P X number of times because we have X successes and the success probability is P. We are multiplying Q N minus X number of times because failures have occurred N minus X number of times and the failure probability is Q. We know from combination that the number of ways in which X items can be selected out of N total items is NCX. For items here we have X and the total number of items we have N. So NCX is the number of ways in which X successes can be achieved in N number of trials. So by addition law of probability, the required probability of X number of successes in N number of trials will be P power X into Q power N minus X added NCX number of times. And that is how we get this probability mass function of the binomial random variable. In simple words, the total number of scenarios for X successes and N minus X failures is NCX. And these cases are mutually exclusive and exhaustive, and therefore by the probability addition law of probability we get this probability mass function, and that is how we understand intuitively how to derive the probability mass function of the binomial random variable. Let us see why binomial random variable is called so. Look at this expansion of q plus p the whole power n given by q power n plus nc1 q power n minus 1 p plus nc2 q power n minus 2 p square and so on, ncx q power n minus x p power x plus etc. up to p power n. This is the binomial expansion of q plus p the whole power n. It's binomial because there are two terms, sum of two terms raised to the power of a positive integer. In this binomial expansion, the general term happens to coincide with the probability function of this random variable, and that is why the random variable here is called as binomial random variable, because of the probability mass function coinciding with the general term of the binomial expansion. We call it like that. Let us try to understand the probability mass function of the binomial random variable by taking a simple problem. Let's consider the problem of throwing at a target. Either we can hit the target for which the probability can be taken as P, or we may miss the target, the probability for which we can take as Q. It is a Bernoulli experiment because we either hit or miss, and there is nothing other than hit or miss. In particular, for better comprehension, let us look at the problem of finding the probability of 3 hits and 5 throws. If hits is taken to be success, then we are looking for how many successes here? 3 successes. In how many throws? 5. Throw is nothing but a trial. So we have a clear-cut case where there is a specific number of successes, 3, in a specific number of trials, 5. Therefore, the problem can be done using the binomial distribution. But I would like to do it using the basic principles of probability and not by using the binomial random variable. We know from combinatorics that for 5 trials and each trial with 2 possible outcomes, the total number of exhaustive scenarios will be 2 power 5, and all these 2 power 5, that is 32 scenarios, I have given in the next slide. Observe that the 2 power 5 scenarios, that is 32 scenarios, are given here in the table. In the first case, we find that the first throw results in a hit, the second also results in a hit, so on up to the last throw. That is, all 5 throws have resulted in hitting the target, which means there has been no failure at all. This probability is given by P into P 5 times, that is P power 5. In the next scenario, we have 4 hits followed by a failure, that is miss. Therefore, the probability is P power 4 into Q. Similarly, all cases have been written here. Now, what are we interested in our problem? To find the scenarios where there are 3 hits. Now, I told you that every binomial random variable's value will give us dual information. When we say 3 hits in 5 trials, it automatically implicitly means that 2 have been failures, which means we are looking for those cases where there are 3 hits and 2 failures. That is, in cases where the probability is P cube Q square, which has been highlighted in the table. And we find that the highlighted cases count to 10. Scenario 4, scenario 6, and if we count all the highlighted cases, we find that it is 10. All these 10 scenarios, that is scenario 4, scenario 6, so on up to scenario 25, are mutually exclusive and exhaustive for 3 successes in 5 trials, and therefore we add the probabilities, that is P cube Q square plus P cube Q square 10 number of times, because there are 10 scenarios, to get 10 P cube Q square. So this is the final answer to the problem that was taken. The probability of getting 3 successes out of 5 trials is 10 P cube Q square. Observe that we have got this result by using the axioms of probability and not by using the binomial random variables mass function. If we were to use the binomial's mass function, for n we have 5 and for x we have 3, so that we get 5c3 p power 3 q power n 5 minus 3, giving us 10 p cube q square, which coincides with the earlier answer that we had got. Does it mean that every problem can be solved directly by using the basic rules of probability and we don't have to use the binomial random variable? That is not the case, because in this enumeration technique, the problem's magnitude becomes bigger for bigger number of trials. When we take 6 trials, we find that the number of exhaustive cases are 2 power 6, that is 64. When we take 7 trials, the number of exhaustive cases will be 2 power 7, that is 128. So the problem magnifies in its size when we take the trial values as a higher number. I have taken 5 for better comprehension, and the problem is manageable because we have only 32 scenarios. So as the number of trials keep increasing, the scenario count also increases, and therefore this is not a good method of solving a problem. See that using the binomial random variables mass function, the problem gets solved very easily. Here I have taken 2 different examples. I have taken the probability of hit to be 0.4 and the probability of miss to be 0.6. So for 3 successes in 5 trials, by a direct application of the mass function, the probability is 0.2304, that is 23% chance. By taking the hit probability as 0.7 and the miss probability as 0.3, for the same 3 success in 5 trials problem, the probability is 0.3087 or 31%. So by increasing the probability of hit from 0.4 to 0.7, we find that there is an increased probability in 3 successes out of 5 trials from 23% to 31%. Now let us look at the Poisson distribution. Its mass function is given by e power minus lambda, lambda power x by x factorial, x taking value 0, 1, 2, 3, so on. I would want to talk about lambda a little later. Look at the distinct feature of the Poisson distribution, unlike the binomial distribution. In binomial, x took values from 0 to n, but here x takes values from 0, 1, 2, 3, so on. That is, the Poisson random variable characterizes a specified number of successes in large number of Bernoulli trials, in a big number of Bernoulli trials. And also, the probability of success P must be very small when compared to the probability of failure Q. As such, P and Q are probabilities, therefore they lie between 0 and 1. If in a problem we find that the probability of success is skewed towards 0 and the probability of failure is skewed towards 1 and n is a large number, Poisson distribution can be used. In very simple words, the Poisson distribution is a limiting form of the binomial distribution under the limit condition specified here. N, the number of trials must be indefinitely large. P, the probability of success must be very small when compared to the probability of failure. The third condition says the mean n into p equal to lambda must be finite. For the binomial random variable, the mean is given by n into p, and this n into p is what is represented by lambda, and that is what we find here in the mass function. This lambda has to be a finite number. The first and the second limiting conditions automatically give us a third condition. If n is a large positive integer and p is a small fractional number lying between 0 and 1, automatically the product of n and p will be finite, which means this limiting condition is only because of number 1 and number 2 conditions. Let us see how one can derive the probability mass function of the Poisson random variable, starting with the binomial mass function by incorporating the limiting conditions. We know n into p is equal to lambda, which means p is equal to lambda by n. Also, p plus q equal to 1, which means q is equal to 1 minus p. So the p here is replaced with lambda by n using equation number 1. The q here is replaced with 1 minus p, and that p is once again written as lambda by n. And we know that NCX is given by the formula n into n minus 1 into so on up to n minus of x minus 1 divided by x factorial. Now lambda by n the whole power x can be rewritten as lambda power x by n power x. 1 minus lambda by n the whole power n minus x can be written as a product of 1 minus lambda by n the whole power n into 1 minus lambda by n the whole power minus x. I have just made a few rearrangements of terms. I have taken lambda by lambda power x and x factorial together, and this n power x has been taken in the place of the x factorial. That is just a simple rearrangement of the terms in the product. Now in the numerator, we find this n minus 1. I take n outside to get n into 1 minus 1 by n. In this n minus 2, I take an n outside to get 1 minus 2 by n inside. Like this, I keep doing up to the n minus of x minus 1th term. Now, if all these n's were to be taken outside, we get a product of n's. How many n's do we get? This represents the first n. This is the second n. This is the third n. And if you keep counting, this is the x minus 1th n. Which means we take a product of x minus 1 n's, that is n power x minus 1. There is already an n here. N into n power x minus 1 we know is n power x. This n power x and n power x get cancelled and we get this final statement. Let us call this statement as equation number 2 and introduce limit on either side of equation 2. Here lambda power x divided by x factorial is taken outside because it is independent of n. And then we apply the limit on each of the terms in the product, that is on 1 minus 1 by n, 1 minus 2 by n, 1 minus 3 by n, and so on up to the last term. Now here 1 by infinity is 0, 1 minus 0 is 1. That's how you get this 1. 2 divided by infinity is 0, 1 minus 0 is 1 to get this. 3 by infinity is 0, 1 minus 0 is 1, and that's how you get this. If you keep continuing until the last term here, x minus 1 divided by infinity is 0, 1 minus 0 is 1. And then we have these two terms. But we know from calculus that limit 1 minus lambda by n the whole power n is e power minus lambda, that is this term. And limit 1 minus lambda by n to the power of minus x when n tends to infinity is 1. So when you substitute all this, we get e power minus lambda, lambda power x by x factorial, which is precisely the probability mass function of the Poisson random variable. So on the left hand side, we have the probability mass function of the binomial random variable, and as n tends to infinity limit, we find that it reduces to the Poisson random variable, which evidently means that the Poisson random variable is after all a limiting condition of the binomial random variable under the limit conditions that the number of trials n is large and the probability of success p is very small. Some of the practical situations where Poisson distribution can be used is in cases where the probability of death from a pandemic and its related number, the probability of suicides and its related number, probability of defective material. One can see from the examples given here that Poisson distribution is used in all those cases where the success is a very rare event, which means that the probability of success is very small. An event that frequently occurs, the probability will be high for it. So Poisson distribution, in other words, can be said to characterize the probability of very, very rare events in a large number of trials. A distinguishing feature of the binomial distribution is that the mean must be greater than the variance, and for the Poisson distribution, the mean must be equal to variance. It's a very important property of binomial and Poisson, and that I will emphasize using a few examples in the slides to come. Look at this particular example. A life insurance company has assessed that the probability of a septuagenarian to die from a disease is 0.00005. What will be the probability that out of 20,000 septuagenarian policy holders, the company must settle more than 2 claims? A septuagenarian is a person of the age between 70 and 79. The probability for such a person to die is assessed to be 0.00005. And such septuagenarian policy holders are 20,000 in number. We are asked to find the probability for more than 2 claims. A life insurance company will settle a claim when a person, that is a policy holder, dies, which means the number of claims here is nothing but the number of people, septuagenarian policy holders, who die. Now the probability for such a person to die is 0.00005, which is a very small number skewed towards 0, and the number of policy holders, that is number of trials, is 20,000, and that's a fairly large number. Therefore we design the problem using the Poisson distribution. So the probability of a person to die is P. Automatically for him not to die is Q, which is obtained by using P plus Q equal to 1. Observe that P is very close to 0 and Q is very close to 1. N is 20,000. Look at the link between P and X. If P is the probability of a septuagenarian to die, then X is the number of septuagenarians who die. That is the number of claims. That is a direct link between P and X. Lambda can be evaluated using the formula N into P, and that happens to be 1 in this case. I have already given you why it is solved using Poisson. By a direct application of the mass function, we can solve the problem. More than 2 claims means X must take values greater than 2. Greater than 2 indicates 3, 4, 5, so on up to infinity. We can evaluate up to infinity, therefore we take its complementary event. For greater than 2, the complementary is less than or equal to 2. Less than or equal to 2 means x equal to 0, x equal to 1, and x equal to 2. By directly solving using the mass function and the calculator, we find the required probability to be 0.0803. One really wishes that the deaths because of corona also is as low probable as the one that we have done here. If the same problem had to be solved by the binomial distribution, look at what would have happened. N is 20,000, P is 0.00005, and Q is 0.99995. By directly using the same methodology, we find that we get 0.0803, which exactly coincides with the Poisson approximation for the probability. Now, does it indicate that a problem can be solved alternatingly with the Poisson distribution and binomial distribution? Please hold your thought. In this particular problem, it was possible. I can give you the reason for that. For the present problem, the mean n into p is 1 and the variance n into p into q is 0.99995. In actuality, we find that 1 is greater than 0.99995. That is, the mean is greater than variance, which is the characteristic property of the binomial random variable, which means the problem had to be done by using the binomial distribution. But we observe that the mean and variance are almost the same. 1 and 0.9995 are approximately equal to each other, which means the problem can be done even by using the Poisson approximation, and that is why both binomial and Poisson approximation for the probability is the same. That is, the mean and variance do not differ by much. They differ only by a very small margin, 0.00005. That is why both approximations gave us the same answer. But this need not be the case in every problem. Let us look at a counter example. A man takes a step forward with probability 0.4 and a step backward with probability 0.6. Find the probability that at the end of 11 steps he is one step away from the starting point. Observe that the forward probability is 0.4 and the backward probability is 0.6, and on adding it we get 1, which means it's a Bernoulli trial. That is nothing other than forward and backward. That is, the man does not take any step other than forward steps and backward steps. So if P is taken as a probability of man taking forward, then obviously Q is probability for backward. Number of steps taken by him is 11. P and X have a direct relevance. If P is probability of man taking forward step, then X is the number of forward steps taken by the man. Now see that the two scenarios here are like this. Let this be the starting point. From this starting point, the man moves forward 5 times. 1, 2, 3, 4, 5. And after 5 forward steps, he is presently in this position P5. From here, he takes 6 backward steps. 1, 2, 3, 4, 5 and 6 to be in this position finally. We observe that by taking 5 forward and 6 backward, he is one step away from the starting point in the backward direction. Look at scenario number 2. He starts here. He takes 6 forward steps. 1, 2, 3, 4, 5, 6, and then 5 backward steps. 1, 2, 3, 4, 5 to be in this position finally. This position is also one step away from the starting point but in the forward direction. And these are the only two possible cases for the man to be a step away from the starting position. In the first scenario, he is away from the starting position by one step in the forward direction by taking 5 forward and 6 backward. In the second scenario, he is one step away from the starting position in the forward direction by taking 6 forward and 5 backward steps. And these two scenarios are mutually exclusive and exhaustive. So using the binomial distributions mass function, the two scenarios are mutually exclusive and exhaustive. Therefore, we add the probabilities. The scenario number 1 is 5 forward and 6 backward. Scenario 2 is 6 forward and 5 backward. But we have taken x to be the number of forward steps, which is 5 in this case, therefore x equal to 5. 6 in this case, therefore x equal to 6. Please remember that when we say x equal to 5, it automatically means that explicitly 5 forward steps, and implicitly it means the remaining 6 out of 11 have been backward. Dual information in every value of the random variable. So by directly applying the values of x, we find that the probability is 0.3679. This is obtained by using the binomial approximation. If the same problem had to be done using Poisson distribution, lambda we know is n into p, that is 11 into 0.4, that is 4.4. By directly applying the addition theorem once again, for the approximation done using Poisson, we find that the probability is 0.2926, and that does not coincide with the binomial approximation. We find that the answer to the same question on using binomial approximation and Poisson approximation differs. See that the mean in this case is n into p 4.4 and variance n into p into q is 2.64. See that the mean and variance are not even approximately equal to each other. We find mean to be strictly greater than the variance, and that's a characteristic property of binomial random variable, which means the problem is better approximated for the probability using the binomial variable and not using the Poisson variable, which directly means that a problem cannot be done using binomial or Poisson. It has to be done using only one of the two approximations. The cases where any one of the two can be used are those cases where the mean is greater than variance and the mean and variance are approximately equal to each other, though mean is greater than variance. That is, the difference between mean and variance is a very small fractional value. In such cases, we can apply either binomial or Poisson. So we can conclude that in cases where the probability of success is very small, that is a rare event, and the n value is a large number. Poisson approximation is a better approximation than binomial approximation. Let us look at the next random variable, that is geometric random variable, whose mass function is given by q power x minus 1 into p, x taking 1, 2, 3 and so on as values. The other way of defining the probability mass function of geometric random variable is q power x into p, x taking values 0, 1, 2, 3 and so on. Both are correct ways of defining the geometric random variable's mass function. I prefer to use 1, 2, 3 etc. for better comprehension. Recall that the binomial random variable characterizes a specific number of successes in a specific number of Bernoulli trials. Poisson random variable characterizes a specific number of successes in a huge number of trials with the condition that the probability of success is very small. Geometric random variable characterizes the first success in an unspecified number of Bernoulli trials. That is, the Bernoulli trials will keep repeated until the first success is achieved. Once the first success is achieved, the trial is abandoned henceforth. That is, we don't continue with the Bernoulli trial. Why is geometric random variable called so? Recall geometric progression from algebra. If P is the first term and Q is the common ratio, then the terms of the geometric progression are P, Q into P, Q square into P, Q cube into P, so on, Q power x minus 1 into P and so on. We find that the general term here is Q power x minus 1 into P, and that coincides with the probability mass function of the geometric random variable. That is why the random variable is called so. Because the general term of the geometric progression coincides with the mass function of this random variable, it is called as a geometric random variable. Now, when can geometric random variable be used? In all those cases where one is looking for the first success. Typically, writing an examination can be geometric because we don't write after we pass the exam. As when we attempt in the first try, if we pass, we don't write again. If we fail in the first attempt, we write the second time. When we pass, we don't write again. If we fail in 1 and 2 attempts, then we go for the third attempt. So we will keep writing the exam until we get the first success. That is geometric. And then the license test also is an example of a geometric random variable, because once we receive the license, we don't go for the license test again. So if the xth trial resulted in the success, it means the prior x minus 1 trials have resulted in failures, which I have represented in the table here. The first trial has resulted in a failure. The second trial has resulted in a failure, and all the trials up to the x minus 1th trial have resulted in failures, and the xth trial is a success. I have taken the trial count from 1 and not from 0, unlike binomial or Poisson. And that is my way of solving geometric problems. So here, by a direct application of the multiplication law, we find that x minus 1 times failure has occurred. Therefore, it is q into q, x minus 1 number of times, that is q power x minus 1. And the xth trial is a success. Therefore, we have a p. That's how we get q power x minus 1 into p. And that is how we intuitively understand how to derive the probability mass function of the geometric random variable. Look at this example. If the probability of an applicant passing driver's license test is 0.8, find the probability that he gets his license in the 4th attempt or fewer than 4 attempts. We are looking for the probability of the first success in the 4th attempt, indicating that it is the geometric random variable. Observe here that the emphasis in the problem is more on the attempt at which the first success was achieved. So that is given the priority, unlike binomial and Poisson. In binomial and Poisson, we are more interested in the number of successes. Here we are more interested in the number of trials required for the first success. So P, the probability of passing the test, is 0.8. Automatically Q is 0.2. By a direct application of the geometric random variable, we get the required probabilities. In the 4th trial, therefore x is 4. So we find 0.0064. In fewer than 4 trials, x less than 4 automatically, that is 1, 2, 3. Observe 0 is not taken because our trial count started from 1. And we get 0.9920. Let us now look at the negative binomial distribution. Its mass function is given as x minus 1 c k minus 1 p power k q power x minus k, x taking values k, k plus 1, k plus 2 and so on. The negative binomial random variable characterizes the first k successes in a set of Bernoulli trials. It is a generalization of the geometric random variable. Geometric random variable, we look for the first success. Here we look for the first k successes. the number of trials required for the first k successes. So again, like in geometric, unlike in binomial and Poisson, the emphasis is on the number of trials required for the success. If the number of trials required is for the first success, it is geometric. If the number of trials required is for the first k successes, it is negative binomial distribution. See that k here is the required success count, and x is the total number of trials required for achieving the k successes. Now, interestingly, the values taken by the random variable start only from k and not from 0 or from 1, unlike binomial, Poisson and geometric. Very simple reason is, if one wants to achieve k successes, minimum the number of Bernoulli trials has to be k. As a simple example, if I'm looking for 10 successes, I can't perform the trials less than 10 times and look for 10 successes. 10 successes can be achieved in a minimum of 10 trials. 10 successes can be achieved in 10 trials, or 10 successes can be achieved in 11 trials, or 10 successes can be achieved in 12 trials, and so on. One cannot achieve 10 trials in less than 10 successes in less than 10 trials. That is absurd. That is why x takes values from k onwards, k being the required number of successes. The other way of defining the negative binomial random variable is through the number of failures. Here it is through the number of trials required for k successes. Here it is a number of failures y before the kth success occurs. That is using the failure count. This is the mass function for it, minus 1 power y minus k c y p power k q power y. Because we use a negative value here in the combination, the distribution is called as negative binomial distribution. It is a generalization of the geometric distribution, as I told you. Geometric distribution and negative binomial distribution, we are emphasizing on the number of trials required for the first success or the first k successes respectively, unlike binomial and Poisson, which looks for the success and not for the number of trials. In simple words, in binomial and Poisson, we fix the number of trials and count success, whereas in negative binomial and geometric, we fix the number of success and count the trials. A distinct feature of the negative binomial distribution is that the mean is always less than the variance. Now let us try to understand intuitively how to derive the negative binomial distribution's mass function. The kth success occurs in the xth trial, meaning the prior x minus 1 trials have resulted in how many successes? K minus 1 successes. We have a specific number of successes in a specific number of trials, a direct case of binomial distribution. That is, if we leave out the xth trial where the kth success has occurred, all the prior x minus 1 trials can be characterized using the binomial distribution, because we have a specific number of successes and a specific number of trials. So by directly applying the binomial mass function, for n the number of trials we have x minus 1, for r the number of successes we have k minus 1. So by directly using it, we get this probability. Remember that this is the probability for the trials up to x minus 1. What happens in the xth trial? We get a success whose probability is p. So by the multiplication law, the probability up to x minus 1 trials is multiplied with the probability of the xth trial, and that's how you get this result. P power k minus 1 into p automatically gives you p power k, and this is precisely the probability mass function of the negative binomial distribution, and that gives you the derivation for the PMF of the negative binomial distribution. For better comprehension, let us look at the same example that we dealt with in the binomial distribution. We are looking for 3 hits out of 5 throws, with the extra condition that the third hit is happening in the 5th throw. Without this extra condition, the problem is binomial. Observe that we look for 3 successes in 5 throws with the condition that the third success occurs in the 5th throw, meaning that the first 4 throws have resulted in 2 successes or 2 hits, which is binomial. Therefore, we get the probability as 6p square q square. The 6p square q square is the probability up to the 4th trial. We have not taken the 5th trial into consideration. Now for this, we have the exhaustive cases represented in table 2. We have 4 trials, each trial having 2 outcomes, therefore 2 power 4 cases, that is 16 cases. The cases have been enumerated here. What are we looking for? 2 successes and 2 failures. That is, we are looking for p square q square cases, which is 6 in number, and that 6 is nothing but 4c2. this value 6p square q square. Now the fifth trial is a success. Therefore, by multiplication law, we have 6p square q square into p, that is 6p cube q square. Now this we have achieved by using the basic probability condition concepts. By using negative binomial, we get the answer rather very easily, even without using any table or enumeration technique. So this is a better way of solving the problem. Let us look at an example. If the probability is 0.4 for a man exposed to corona will get infected by it, then what is the probability that the 10th man exposed to corona is the third to get infected? We are looking for 10 exposures for the third infection. So the emphasis is on the exposure count, that is trial count. That is why it is negative binomial. Obviously, it is Bernoulli because for infection the probability is 0.4, which means for not getting infection the probability is 0.6. So x is 10, the number of trials required for k successes, k being 3. So by a direct application of the Bernoulli, negative binomial random variables mass function, we get the required result. A rather simple application of the negative binomial distribution. Observe that the probability is 0.0645. Let us look at some practical cases to identify what distribution can be used. A typist types 2 erroneous letters for every 100 letters. What is the probability that the 14th letter is the first erroneous letter? We are looking for the first erroneous letter in the 14th attempt, meaning it is geometric distribution. It was observed from historical data that 1 out of 5 cargo ships capsized in the sea. If 10 cargo ships are on the sea, what is the probability that exactly 6 arrive safely? We are looking for exactly 6 safe arrivals out of 10. That is specific number of successes in specific number of Bernoulli trials. Therefore, it is binomial distribution. In a production unit, a machine is known to produce 3% defective items. What is the probability that 5 items have to be examined for getting 2 defective items? See that the emphasis is on inspecting 5 to get 2 defective. That is, it is more on the number of trials, and therefore the problem is done using negative binomial distribution. If the number of accidents caused by water tanker lorries in a city per month averages 3, what is the probability that out of 1000 lorries operated in a certain month, 5 accidents occur? The number of lorries or the trials is 1000, fairly large. We are given the average, that is mean. If mean is 3, that is n into p is equal to 3, where n is 3000, then p is automatically 3 by 1000. That is probability of success. What will be the probability of failure? 997 divided by 1000, which is very skewed towards 1. And the failure success probability is very skewed towards 0. Therefore, the problem is better approximated by Poisson distribution. A dice is thrown until 6 appears. What is the probability? It must be thrown at least 6 times. We are looking for the first success in the 6th attempt. Therefore, it is geometric random variable. If the probability that a rumor is believed is 0.75, what is the probability that the 8th person to hear the rumor is the third to believe? The probability is emphasized towards the 8th trial for the third belief. Therefore, it is a negative binomial. The probability that an army base can be destroyed by a missile is 0.85. What is the probability that a particular army base will be destroyed in the 5th attempt? We are looking for the first success in the 5th trial, indicating it is geometric distribution. Find the probability that 5 defective items will be found in a box of 2000 items if data shows that 2% of items are generally defective. 2% is the probability of success, that is 2 by 100, very small. Failure is 98 by 100. 2000 is fairly large, therefore Poisson distribution. Hope you have been able to understand the summary. Binomial random variable characterizes specific number of successes in specific number of Bernoulli trials. Poisson characterizes specific number of successes in a large number of Bernoulli trials with the condition that the probability of success is very small. Geometric random variable characterizes the first success in a set of Bernoulli trials. Negative binomial random variable characterizes the first k successes in a set of Bernoulli trials and is a generalization of the geometric random variable. I hope you have been able to understand the 4 distributions and all its facets. Feel free to write to me through these mail IDs if you have any queries. Thank you for your patient listening. All the best.